Welcome to the Sleepy Storyteller, where we drift gently through the universe's most profound mysteries. I'm so glad you're here tonight, wherever you might be listening from. Perhaps you're curled up in bed with the covers pulled close, or maybe you're settling into a favorite chair as the day finally winds down. Wherever you are, I hope you feel comfortable and ready to let your mind wander among the stars. Before we begin our cosmic journey, I'd love to know where in the world you're joining me from tonight. Are you watching from a quiet bedroom in London, listening to the rain tap against your window? Or perhaps you're in a cozy apartment in Tokyo, with the city lights twinkling beyond your curtains. Maybe you're somewhere where in the countryside, the stars above mirror the ones we'll be talking about tonight. Drop a comment and let me know. There's something magical about knowing our little community stretches across the globe, all of us looking up at the same vast sky. If you find these gentle explorations soothing, a like would mean the world to this sleepy little channel. And if you're new here, consider subscribing for more peaceful journeys through space and time. To those of you who've already joined our stargazing family, thank you. Your presence here makes each video feel like sharing stories around a cosmic campfire. Now, I'll try not to make tonight's topic so fascinating that it keeps you wide awake, but if it does, at least you'll drift off with a deeper understanding of how the universe creates its most spectacular endings, and beginnings too, as we'll discover. So settle in, close your eyes if you'd like, and let's embark on a journey that spans billions of years, from the gentle birth of stars to their dramatic final acts. Tonight, we're exploring one of the most beautiful and profound processes in the cosmos: how stars die. It sounds somber, doesn't it? But stellar death is anything but an ending. It's transformation, creation, rebirth. It's the universe's way of recycling its most precious materials, ensuring that the story of light and matter continues across cosmic ages. Every star you see twinkling in the night sky is living on borrowed time, not in a tragic sense, but in the most natural way imaginable. Stars are cosmic engines, burning through their fuel with patient determination, creating the very elements that make planets, trees, and even you possible. They're the universe's alchemists, transforming simple hydrogen into the complex chemistry of existence itself. But like all great stories, a star's tale has chapters: birth, a long and productive middle age, and then, depending on its mass, one of several possible endings. Some stars go gently into that good night, puffing away their outer layers like cosmic dandelions in a celestial breeze. Others rage against the dying of their light in explosions so violent they can outshine entire galaxies for months. Let's begin where all stellar stories must, in the heart of a star, where the magic of fusion creates light and life. Deep within every star lies a furnace beyond imagination. At temperatures reaching millions of degrees, hydrogen nuclei overcome their natural tendency to repel each other and fuse together, creating helium and releasing tremendous amounts of energy. This nuclear fusion is what makes stars shine, what warms planets, what makes life possible across the universe. Picture this cosmic dance happening trillions of times, every second inside our own sun. 4 hydrogen nuclei come together, despite the electromagnetic forces trying to push them apart. The extreme heat and pressure at the sun's core compress these particles until they're forced into an intimate embrace, fusing into a single helium nucleus. In the process, a tiny amount of mass converts directly into energy. Following Einstein's famous equation, that energy begins a journey that can take hundreds of thousands of years to travel from the core to the surface, and then just 8 minutes to reach your skin on a sunny afternoon. For most of a star's life, this process maintains a delicate balance. Gravity tries to collapse the star inward, while the outward pressure from fusion reactions pushes back. It's like a cosmic tug-of-war that can last for billions of years. Our Sun, for instance, has been maintaining this balance for about 4.5 billion years and has roughly another 5 billion years to go before things start getting interesting. But fusion is a hungry process. It consumes hydrogen at rates that would make any earthly fire seem like a gentle candle flame. The Sun converts about 4 million tons of matter into pure energy every single second. 4 million tons, disappearing into light and heat, creating the gentle warmth that makes flowers bloom and oceans flow on our little blue planet. As stars age, they begin to run low on hydrogen in their cores. This is when their stories start to diverge, like paths branching in a cosmic forest. The fate of each star depends primarily on one factor: its mass. How much stellar material it gathered during its birth determines not just how it will live, but how it will die. Smaller stars, those with less mass than our Sun, live remarkably long and peaceful lives. These red dwarf stars burn their hydrogen so slowly and efficiently that they can shine for trillions of years. That's longer than the current age of the universe by a factor of hundreds. In fact, since the universe is only about 14 billion years old, not a single red dwarf star has yet had time to exhaust its fuel and die. They're the tortoises of the stellar world, steady and enduring, outlasting nearly everything else in the cosmos. When these modest stars finally do exhaust their hydrogen, they lack the mass to ignite the fusion of heavier elements. Instead, they simply cool down over astronomical timescales, slowly fading from red to brown to black, becoming stellar embers drifting through space. They end not with a bang, but with a whisper, gradually releasing their heat into the cosmic night until they become cold, dark spheres of spent nuclear fuel. Stars like our Sun have more dramatic endings in store. When a Sun-like star begins to exhaust the hydrogen in its core, gravity starts winning the tug of war. The core contracts and heats up, while the outer layers expand and cool, transforming the star into a red giant. These bloated stellar seniors can grow enormous, sometimes large enough to engulf the orbits of inner planets. During this red giant phase, the star's core eventually becomes hot enough to fuse helium into carbon and oxygen. It's like adding a new log to a dying fire, giving the star a second lease on life. But this helium burning phase is much shorter than the hydrogen burning that came before. Where hydrogen fusion might last 10 billion years, helium fusion lasts only about 100 million years. As the star continues to age, it goes through cycles of expansion and contraction, burning different fuels in concentric shells around its core. It's like a cosmic onion, with different fusion reactions happening at different layers. Helium burns in one shell, while hydrogen burns in another, creating an intricate stellar architecture of nuclear furnaces. Eventually, even stars like our Sun reach the limits of what fusion can provide. They lack sufficient mass to ignite the fusion of carbon and oxygen into heavier elements. At this point, the star faces its final crisis. The core can no longer produce enough energy to support the star's outer layers, and gravity finally wins its ancient battle. But this isn't a violent collapse, at least not yet. Instead, the star gently puffs away its outer atmosphere in beautiful, expanding shells of glowing gas. These are called planetary nebulae, though they have nothing to do with planets. The name comes from early astronomers who thought these round, colourful objects looked like distant planets when viewed through small telescopes. At the centre of this expanding gaseous artwork sits the hot, dense core of the original star, now called a white dwarf. White dwarfs are remarkable objects, about the size of Earth but containing as much mass as the Sun. A teaspoon of white dwarf material would weigh as much as a car. These stellar remnants are so dense that their atoms are crushed together in ways that don't exist anywhere on Earth. White dwarfs shine not from nuclear fusion, but simply from leftover heat. They're like cosmic coals in a dying fire, slowly cooling over billions of years. They start out blindingly hot and white, hence the name, but gradually cool through yellow, red, and eventually to black. The coolest white dwarfs we observe are likely among the oldest objects in the universe, ancient lighthouses whose beams have dimmed to barely perceptible glows. But what about more massive stars? Those giants that gathered much more material during their formation. Their endings are far more spectacular and violent. These stellar titans have enough mass to keep the fusion fires burning through increasingly heavy elements. After exhausting hydrogen, they burn helium. After helium, carbon and oxygen, then neon, then silicon, building up the periodic table, one fusion reaction at a time. This process creates the cosmic foundries where most of the elements heavier than hydrogen and helium are forged. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in the nuclear furnaces of massive stars. You are quite literally made of stardust, assembled from materials that were once part of stellar cores burning billions of degrees hot. The fusion process in these massive stars follows an increasingly desperate rhythm. Each new fuel burns faster and at higher temperatures than the last. While hydrogen burning might sustain a massive star for millions of years, silicon burning lasts only days or weeks. It's like watching a cosmic candle burning from both ends, racing toward an inevitable conclusion. As the star builds up heavier and heavier elements in its core, it creates a layered structure reminiscent of a Russian nesting doll. The outermost layers still burn hydrogen, while deeper shells fuse helium, carbon, oxygen, and silicon in concentric zones of nuclear fire. At the very center, iron begins to accumulate. And iron, as it turns out, is where this beautiful process hits an insurmountable wall. Iron is the most stable element in the universe. Unlike lighter elements, fusing iron doesn't release energy. It actually requires energy input. When a massive star's core becomes dominated by iron, the nuclear furnace that has sustained the star for millions of years suddenly shuts down. No more energy production means no more outward pressure to balance gravity's relentless inward pull. What happens next unfolds with breathtaking speed. The iron core, roughly the size of Earth but containing more mass than the Sun, collapses in less than a second. In that brief moment, the core shrinks from thousands of kilometers across to perhaps 20 kilometers. The matter becomes so compressed that protons and electrons are squeezed together to form neutrons, creating the densest stable matter known in the universe. This collapse releases an enormous amount of gravitational energy, more than the star has produced through fusion during its entire lifetime. The energy is so intense that it reverses the inward fall of the star's outer layers, creating a shockwave that races outward through the stellar material at thousands of kilometers per second. The result is one of nature's most magnificent spectacles, a supernova explosion. For a few brief months, this single dying star can outshine the combined light of all the other stars in its galaxy. The explosion is visible across intergalactic distances, a cosmic lighthouse beacon announcing the dramatic end of a stellar giant. But supernovas are more than just spectacular light shows. They're the universe's way of seasoning space with heavy elements. The explosion hurls the star's outer layers, rich with the elements forged during its lifetime, into the surrounding interstellar medium. These materials, dispersed by the violence of the star's death, become the raw ingredients for future generations of stars and planets. Every element heavier than iron in the periodic table is created not during a star's life, but in the extreme conditions of its death. The gold in jewelry, the silver in coins, the uranium in nuclear reactors, all were forged in the incredible heat and pressure of supernova explosions, or in the collisions between the ultra-dense objects they leave behind. At the center of the explosion, where the original star's core collapsed, something extraordinary remains. If the original star was between about 8 and 20 times more massive than our Sun, the collapsed core becomes a neutron star. These objects are almost beyond comprehension. A neutron star contains more mass than the Sun compressed into a sphere only about 20 kilometers across. They're so dense that a sugar cube of neutron star material would weigh about as much as Mount Everest. Neutron stars spin rapidly, often hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. Some of them sweep beams of radiation across space like cosmic lighthouses, appearing to pulse on and off as their beams sweep past Earth. We call these pulsars, and they keep time with an accuracy that rivals the best atomic clocks. The surface of a neutron star would be a landscape beyond imagination. Gravity there is so strong that if you could somehow stand on it, you would weigh about 100 billion times more than you do on Earth. The magnetic fields would instantly rearrange the atoms in your body. The surface itself might be made of a crystalline lattice of atomic nuclei, surrounded by a sea of free neutrons, creating the strangest solid material in the universe. But what happens when an even more massive star dies? When the original star contained more than about 20 or 25 times the mass of our Sun. In these cases, not even neutron degeneracy pressure can halt the gravitational collapse. The core continues falling inward past the neutron star stage, shrinking smaller and smaller as gravity overwhelms every known force that might stop it. At some point, the collapsing matter crosses what physicists call the event horizon. This is the boundary around a black hole beyond which nothing, not even light itself, can escape. The formation of a black hole represents perhaps the most extreme transformation possible in our universe. Matter that once powered a star visible across thousands of light years disappears behind an invisible boundary in space. Black holes challenge our understanding of physics in fundamental ways. At their centers lies something called a singularity, where the normal rules of space and time break down completely. The matter that formed the black hole is compressed to infinite density in zero volume, creating conditions that our current physics cannot adequately describe. Yet despite their fearsome reputation, black holes play crucial roles in the cosmic ecosystem. They help regulate star formation in galaxies, and their gravitational influence shapes the large-scale structure of the universe. Supermassive black holes, millions or billions of times more massive than the Sun, lurk at the centers of most galaxies, including our own Milky Way. The space immediately around a black hole is anything but empty. Matter falling toward the event horizon forms what's called an accretion disk, a swirling maelstrom of superheated gas that can shine more brightly than entire galaxies. The intense gravity near a black hole stretches and compresses this infalling material, heating it to temperatures of millions of degrees and causing it to emit intense radiation across the electromagnetic spectrum. These cosmic whirlpools can launch jets of particles at nearly the speed of light, shooting out from near the black hole's poles like searchlight beams extending for thousands of light years. These jets carry tremendous amounts of energy and can trigger star formation in distant regions of a galaxy, creating a feedback loop between stellar death and stellar birth. Perhaps most remarkably, black holes aren't truly black. According to quantum mechanics, they actually emit a faint radiation called Hawking radiation. This process is incredibly slow for stellar mass black holes. They would take longer than the current age of the universe to evaporate completely. But it suggests that even these most permanent-seeming objects in the universe are not eternal. The radiation arises from quantum fluctuations near the event horizon, where pairs of virtual particles spontaneously appear and disappear throughout space. Near a black hole, sometimes one particle from such a pair falls past the event horizon, while the other escapes, creating the appearance that the black hole is slowly radiating away its mass. This leads to a beautiful paradox. Smaller black holes actually evaporate faster than larger ones. A black hole with the mass of a mountain would evaporate in less than a second, while one with the mass of the Sun would take longer than the universe has existed to disappear completely. The most massive black holes in the universe will be among the last objects to fade away, slowly evaporating over timescales so vast they make stellar lifetimes seem like brief flickers. The study of stellar death, has revealed something profound about the nature of the universe itself. Death and birth are intimately connected on cosmic scales. The spectacular endings of massive stars seed space with the elements necessary for planets and life. The energy released in supernovas can trigger the formation of new stars in nearby gas clouds. Even black holes, those seeming endpoints of matter, play active roles in regulating star formation and galaxy evolution. In a sense, every star carries within it the seeds of its own transformation. The nuclear processes that give stars their light and warmth also determine their ultimate fate. Mass is destiny in the stellar world, setting each star on a path toward one of several possible endings, from the gentle fade of a white dwarf to the violent birth of a black hole. This cosmic recycling has been going on for billions of years. The Sun itself is likely a second or third generation star, formed from materials enriched by the deaths of previous stellar generations. The heavy elements that make planets like Earth possible were forged in the hearts of stars that died long before our solar system was born. Looking up at the night sky, it's humbling to realize that we're witnessing different stages of this grand stellar cycle all at once. That bright blue star in Orion's belt is burning through its fuel at a furious pace, destined for a spectacular supernova explosion in perhaps a few million years. The dim red star, barely visible to your naked eye, might be a white dwarf, the ancient remnant of a star that died when the universe was young. And somewhere between these extremes, countless stars are quietly fusing hydrogen in their cores, maintaining that delicate balance between gravity and nuclear fire. The diversity of stellar deaths creates a rich tapestry of cosmic phenomena. Some stars don't fit neatly into the categories we've discussed. Stars that exist right on the borderline between different fates can produce hybrid outcomes, creating objects that challenge our understanding of stellar evolution. A star might begin to form a neutron star, but lack quite enough mass to complete the process, resulting in something between a white dwarf and a neutron star that we're only beginning to understand. Then, there are the truly exotic stellar deaths, binary star systems, where two stars orbit each other in a cosmic dance, can produce some of the most spectacular endings imaginable. Picture two massive stars, each burning through their fuel at slightly different rates. When the more massive star begins to die first, it can strip material from its companion, creating streams of hot gas flowing between the two objects like stellar waterfalls. In some cases, one star becomes a white dwarf while its companion continues to burn normally. The white dwarf's intense gravity can slowly steal material from its partner, accumulating hydrogen and helium on its surface. When enough material builds up, it can ignite all at once in a thermonuclear explosion called a nova. These events can make a star suddenly appear 100,000 times brighter, creating what ancient astronomers thought was a new star appearing in the sky. But binary systems can produce even more dramatic endings. If both stars are massive enough to form neutron stars, their orbital dance gradually tightens as they lose energy to gravitational waves, ripples in space-time itself. Eventually, these ultra-dense objects spiral into each other and merge, creating kilonova explosions that forge many of the heaviest elements in the universe. The platinum in catalytic converters, the gold in electronics. Much of it was created not in supernovas, but in these incredibly rare and violent neutron star collisions. The detection of gravitational waves from such mergers has opened an entirely new window into stellar death. These ripples in space-time carry information about the final moments of stars in ways that light never could. When neutron stars collide billions of light years away, the distortions they create in space-time are so subtle that they change distances on Earth by less than 1/10,000th the width of a proton. Yet we can measure these tiny fluctuations, allowing us to witness the most extreme events in the universe. Sometimes the cosmic recycling process produces unexpected results. Certain types of supernovas, called Type 1a, occur when a white dwarf in a binary system accumulates enough material from its companion to exceed a critical mass limit. The entire white dwarf undergoes explosive nuclear fusion all at once, completely destroying the star in a blast so consistent that astronomers use these explosions as cosmic lighthouses to measure distances across the universe. These standardized candles helped reveal one of the most startling discoveries in modern cosmology. By measuring the brightness and redshift of distant Type Ia supernovas, astronomers discovered that the expansion of the universe is accelerating. Something called dark energy appears to be pushing space itself apart at an ever-increasing rate, overwhelming the gravitational pull of all the matter in the universe. This discovery links stellar death to the ultimate fate of the cosmos itself. If dark energy continues to dominate, the universe will expand forever, gradually growing cold and empty as stars exhaust their fuel and no new ones form. The era of stellar death we're witnessing now may represent just the beginning of a much longer cosmic twilight, where black holes slowly evaporate and the universe fades into darkness. But stellar death also offers hope for renewal. Even as old stars die, new ones continue to form in stellar nurseries scattered throughout galaxies. These nebula regions, often enriched by the deaths of previous stellar generations, collapse under their own gravity to birth new stars with higher concentrations of heavy elements. Each successive generation has better raw materials to work with, potentially creating more complex planetary systems. Our own solar system bears the fingerprints of this cosmic recycling. The rocky planets like Earth could only form because earlier generations of massive stars had already forged silicon, iron, and other heavy elements through nuclear fusion and explosive death. The water in our oceans contains oxygen from stellar cores and hydrogen from the Big Bang itself. We exist because stars learned how to die in ways that scattered their treasures across space. The study of stellar death has also revealed the incredible creativity of the universe. White dwarfs can form crystalline structures as they cool, essentially becoming cosmic diamonds the size of Earth. Neutron stars might contain exotic states of matter that we can't create in any laboratory, with cores that could be made of strange quarks or other particles that exist nowhere else. Black holes connect to fundamental questions about the nature of information, time, and reality itself. Even the timescales involved in stellar death inspire a different perspective on existence. A star like our Sun will spend about 10 billion years on the main sequence, burning hydrogen in its core. That's roughly twice the current age of Earth, and longer than life has existed on our planet. From a stellar perspective, the entire history of life on Earth, from the first simple cells to human civilization, represents just a brief moment in the middle of the Sun's stable lifetime. This cosmic perspective doesn't diminish the significance of shorter timescales, but rather places them in context. The mayfly that lives for a single day experiences a complete life cycle within its allotted time. Similarly, stars make the most of their billion-year lifespans, creating light and heavy elements and shaping the structure of galaxies. Even the briefest supernova explosion, lasting only months, can influence star formation across an entire galactic region for millions of years afterward. The violence of stellar death might seem destructive, but it's actually profoundly creative. Supernovas don't just destroy stars, they create conditions necessary for future complexity. The shockwaves from stellar explosions compress nearby gas clouds, triggering the formation of new stars. The heavy elements scattered by dying stars become the building blocks of planets, and potentially life itself. Consider the iron in your blood. Every atom of it was forged in the core of a massive star that died in a supernova explosion billions of years ago. That iron traveled through space for eons before being incorporated into the dust cloud that eventually formed our solar system. It was then gathered into our planet, dissolved in ancient oceans, taken up by primitive life forms, and eventually became part of the hemoglobin that carries oxygen through your veins. This connection between stellar death and biological life runs deeper than just chemical elements. The energy that powers most life on Earth ultimately comes from nuclear fusion in the sun's core. Plants capture this stellar energy through photosynthesis. Animals eat plants or other animals, and the entire food web depends on the steady output of our nearest star. In a very real sense, we're all powered by controlled stellar death, the gradual consumption of hydrogen that will continue for billions of years. The relationship between stellar death and life extends beyond our own planet as well. Astronomers have discovered thousands of exoplanets orbiting other stars, and many of these worlds might harbor conditions suitable for life. The habitability of these distant planets depends largely on the characteristics of their host stars, which in turn are determined by stellar mass and age. Red dwarf stars, those long-lived, low-mass stellar tortoises we discussed earlier, present an interesting case. Their extremely long lifespans mean that planets orbiting them could potentially support life for trillions of years, far longer than Earth's remaining time with the Sun. However, these stars also tend to produce powerful flares that could strip away planetary atmospheres. The relationship between stellar properties and planetary habitability remains an active area of research. More massive stars, while short-lived, create the heavy elements necessary for rocky planets and complex chemistry. There's a balance in the cosmos between stellar longevity and element production. The stars that live longest produce the fewest heavy elements, while the stars that create the richest chemistry die the most quickly. This balance helps determine where and when in the universe's history life might be most likely to emerge and thrive. The timing of stellar death also plays a crucial role in the broader story of cosmic evolution. In the early universe, when it was less than a few 100 million years old, the first stars were very different from the ones we see today. These primordial giants contained almost no heavy elements, just hydrogen and helium left over from the Big Bang. They were likely much more massive than most modern stars, perhaps hundreds of times the mass of our Sun. These first stellar pioneers lived fast and died young, exploding as supernovas after just a few million years. But their brief lives were transformative for the universe. They were the first cosmic alchemists, creating and scattering carbon, oxygen, silicon, iron, and other elements that had never existed before. Without their sacrificial deaths, the universe would have remained a simple place of hydrogen and helium, incapable of forming planets or supporting the complex chemistry that makes life possible. The deaths of these population 3 stars, as astronomers call them, marked the end of the universe's dark age. Their explosions not only enriched space with heavy elements, but also created the first sources of ultraviolet light capable of rayonizing the hydrogen that filled space. This cosmic dawn transformed the universe from an opaque fog into the transparent medium we observe today, as successive generations of stars lived and died. Each wave of stellar death increased the heavy element content of the universe. Astronomers can actually trace this chemical enrichment by studying stars of different ages. The oldest stars in our galaxy contain only tiny traces of elements heavier than hydrogen and helium, while younger stars, like our Sun, have much higher concentrations of these materials. This gradual enrichment process had profound implications for planet formation. The earliest planetary systems, formed around first and second generation stars, would have been very different from our own. Without sufficient quantities of silicon, iron, and other rocky materials, these systems might have contained only gas giants similar to Jupiter and Saturn. The small, rocky worlds, where life as we know it could take hold, required billions of years of stellar death and rebirth to accumulate the necessary building materials. The process continues today, though at a much slower pace than in the universe's youth. Modern stars form from gas clouds that are already enriched with heavy elements, allowing them to create planetary systems with diverse compositions. Some exoplanets discovered by astronomers contain much higher concentrations of heavy elements than Earth, suggesting they formed around stars that had been particularly well fed by previous generations of stellar death. But stellar death doesn't just create raw materials for future worlds, it also shapes the large-scale structure of galaxies themselves. Supernova explosions inject enormous amounts of energy into the interstellar medium, creating hot bubbles of gas that can expand for millions of years. These superbubbles, as they're called, can grow so large that they break through the disk of a galaxy, allowing hot gas to flow out into intergalactic space. This process of galactic winds, driven by stellar death, helps regulate star formation on galactic scales. When too many massive stars form and explode in a short time, their combined energy output can blow away the gas needed to form new stars, temporarily shutting down star formation in that region. It's a cosmic feedback mechanism that prevents galaxies from converting all their gas into stars too quickly. The energy from stellar explosions also creates some of the most beautiful structures in the night sky. Supernova remnants, the expanding shells of gas and dust left behind by exploded stars, can glow for thousands of years as they plow through the surrounding medium. The Crab Nebula, visible through small telescopes in the constellation Taurus, is the remnant of a supernova explosion observed by Chinese astronomers in the year 1054. At the center of this ghostly shell lies a rapidly spinning neutron star, the compressed heart of the original massive star. These supernova remnants serve as cosmic particle accelerators, using magnetic fields to accelerate charged particles to incredible energies. Some of the highest energy cosmic rays detected on Earth may have been accelerated in these stellar graveyards, carrying energy levels millions of times higher than the most powerful human-built particle accelerators can achieve. The magnetic fields around neutron stars create some of the most extreme conditions in the known universe. Magnetars, a special class of neutron stars with magnetic fields trillions of times stronger than Earth's, can experience starquakes so violent that they crack the neutron star's incredibly dense crust. These events release more energy in a fraction of a second than our sun produces in an entire year, creating brief but intense bursts of gamma rays that can be detected across the universe. Even in death, or perhaps especially in death, stars continue to surprise us. Some neutron stars appear to be made of the most perfect fluid known to science, with viscosity billions of times lower than water. Others might contain exotic forms of matter that exist nowhere else in the universe, where the normal structure of atoms breaks down completely and quarks flow freely like a subatomic soup. The study of these extreme stellar remnants pushes physics to its limits. The conditions inside neutron stars are so extreme that they serve as natural laboratories for testing theories about fundamental forces and the behavior of matter under conditions we could never recreate on Earth. Each new observation of a pulsar or magnetar provides insights into physics that might otherwise require centuries to discover through earthbound experiments. Black holes present even more profound mysteries. Despite decades of study, we still don't fully understand what happens to information that falls past an event horizon, or whether the singularities at black hole centers actually exist, or are simply limits of our current understanding. The recent detection of gravitational waves from merging black holes has opened new ways to study these enigmatic objects, revealing details about their formation and evolution that were previously hidden. The images of black holes captured by the Event Horizon Telescope show the glowing accretion disk around these cosmic giants, providing visual confirmation of theoretical predictions made decades ago. The shadow cast by the event horizon appears exactly as Einstein's equations suggested it would, offering powerful confirmation that our understanding of gravity and spacetime remains accurate even under the most extreme conditions. Perhaps most remarkably, the death of stars has given rise to entirely new ways of observing the universe. Gravitational wave astronomy, made possible by detecting the spacetime ripples created when black holes and neutron stars collide, provides information completely independent of electromagnetic radiation. These cosmic collisions create signals that carry details about the internal structure of the most dense objects in the universe, details that light could never reveal. The multi-messenger astronomy that combines gravitational waves with traditional observations has already led to groundbreaking discoveries. When astronomers detected gravitational waves from a neutron star collision, they were able to point optical telescopes at the same region of sky and observe the kilonova explosion that followed. This single event provided direct evidence that neutron star mergers are responsible for creating many of the heaviest elements in the periodic table. Future observations promise even more revelations about stellar death. The James Webb Space Telescope can peer deeper into space and back in time than ever before, potentially further observing the deaths of the very first stars in the universe. These observations could reveal how stellar death has evolved over cosmic time, and how the first heavy elements were distributed throughout the early universe. Ground-based telescopes are also becoming more sophisticated in their ability to study stellar death. Automated survey programs can now monitor millions of stars simultaneously, catching supernovas as they explode and tracking their evolution in real time. These observations are revealing that stellar death is even more diverse than previously imagined, with some stars producing explosions that don't fit neatly into traditional categories. The connection between stellar death and the broader cosmos extends to the very fate of the universe itself. The accelerating expansion driven by dark energy means that star formation will gradually decline as galaxies drift apart and gas becomes too diffuse to collapse into new stars. Eventually, the universe will enter what cosmologists call the stelliferous era, when stellar death will no longer be balanced by stellar birth. But even this cosmic twilight won't mark the end of stellar influence. White dwarfs will continue cooling for trillions of years, potentially serving as the last sources of usable energy in a universe grown cold and dark. Brown dwarfs, failed stars that never achieved nuclear fusion, might occasionally flare to life as they capture stray matter, creating brief moments of warmth in the cosmic winter. The longest-lived remnants of stellar death will be the black holes. As the universe expands and cools, these gravitational monsters will slowly evaporate through Hawking radiation. But the process is so slow that the largest black holes won't disappear until the universe is unimaginably old. In a sense, they represent the final chapter in the story of stellar death, the last whispered echoes of ancient stellar giants. Throughout this vast cosmic timeline, from the first stellar explosions in the early universe to the final evaporation of black holes in the far future, stellar death remains one of the most creative and transformative processes in nature. It's a reminder that endings are also beginnings, that destruction enables creation, and that even in the vast coldness of space, death gives rise to beauty, complexity, and ultimately to life itself. The stars that shine above you tonight are all at different stages of this grand cycle. Some are young and energetic, burning through their fuel with the enthusiasm of cosmic youth. Others are middle-aged and steady, like our own sun, maintaining their nuclear fires with the patience of cosmic maturity. A few are elderly giants, swollen and red, preparing for their final transformation. And scattered throughout the galaxy are the remnants of stars that have already completed their journeys. White dwarfs cooling slowly in the darkness, neutron stars spinning with metronomic precision, and black holes warping space-time with their invisible presence. Each represents a different path through stellar death, a different way that matter and energy can be recycled into new forms and new possibilities. This cosmic dance of stellar death and rebirth has been playing out for over 13 billion years, each act more complex than the last. The universe began as a stage set with only the simplest props, hydrogen and helium left over from the Big Bang. But through the patient work of countless stellar generations, that sparse cosmic theatre has been decorated with the full periodic table of elements, each one forged in stellar furnaces or scattered by stellar explosions. The beauty of this process lies not just in its grandeur, but in its intimacy. the calcium strengthening your bones at this very moment was once part of a massive star's final explosive breath. The oxygen molecules you're breathing were exhaled by dying stars billions of years ago. Even the carbon atoms that form the backbone of every organic molecule in your body were assembled in stellar cores burning at temperatures that would vaporize planets. There's something profoundly comforting about this connection. You are not separate from the cosmos, observing it from the outside. You are the cosmos, temporarily arranged into a pattern capable of contemplation. Every atom in your body has traveled an incredible journey, from stellar birth through stellar death, through the cold depths of space, through the formation of our solar system, and finally into the remarkable configuration that is you. The heavy elements that make complex chemistry possible have their own stories of stellar death. Gold, for instance, requires conditions so extreme that it's primarily created when neutron stars collide, their merged cores becoming factories for the heavier stable elements. The gold in wedding rings and electronic circuits carries within it the memory of one of the most violent events in the universe, two stellar corpses spiraling into each other in a cosmic embrace that literally shook space-time itself. Platinum group metals, essential for catalytic converters and fuel cells, tell a similar story of extreme stellar death. These precious materials were forged in the incredible pressures and temperatures of kilonova explosions, then scattered through space to eventually be gathered into planets like Earth. Every time you start a car, you're relying on elements that were created in some of the most energetic events the universe can produce. Even more exotic elements, the ones that exist only briefly in laboratories before decaying, hint at stellar processes we're only beginning to understand. The heaviest elements in the periodic table, those with names like flerovium and moscovium, probably exist naturally only in the most extreme stellar deaths, perhaps in the cores of colliding neutron stars, or in the final moments before matter disappears behind a black hole's event horizon. The distribution of these elements throughout the galaxy tells a story of stellar death that spans billions of years. The oldest stars, formed when the universe was young, contain almost no heavy elements. They're composed of nearly pure hydrogen and helium, pristine remnants of the cosmos' simpler youth. As you move to progressively younger stellar populations, the heavy element content increases, marking the gradual enrichment of space through countless stellar deaths. Our own sun sits somewhere in the middle of this chemical timeline. It contains enough heavy elements to support rocky planets and complex chemistry, but not so many that planetary systems would be dominated by massive, volatile worlds. We exist in what astronomers call the galactic habitable zone, a region of our galaxy where stellar death has proceeded just long enough to create suitable conditions for life, but not so violently as to sterilize planets with frequent supernova explosions. This cosmic Goldilocks principle extends to time as well as space. We live during what might be called the universe's golden age of habitability. Star formation is still active, providing energy sources and continuing to enrich space with heavy elements. But the violent stellar death that characterized the universe's youth has settled into a more gentle rhythm. Galaxies have had time to develop stable structures, and the heavy element content is high enough to support complex chemistry. Looking toward the future, this golden age won't last forever. As the universe continues to expand and cool, star formation will gradually decline. The raw materials for new stars will become increasingly dispersed, making it harder for gravity to gather enough matter to ignite nuclear fusion. Eventually, perhaps in 1 trillion years, the last new stars will form, and the universe will begin its long slide toward the stelliferous era's end. But even in this far future, stellar death will continue to shape the cosmos. The longest-lived red dwarf stars will continue burning their hydrogen fuel for trillions of years, outlasting not just all other stars, but potentially all other large-scale structures in the universe. These stellar tortoises will be the last lights in a cosmos growing ever darker and colder. When these final red dwarfs eventually exhaust their fuel, they'll join the growing population of white dwarf stars cooling slowly in the darkness. These stellar embers will continue to radiate heat for an almost unimaginable length of time. A white dwarf with the temperature of today's sun will take longer than the current age of the universe, just to cool to the temperature of today's Earth. The coolest white dwarfs will continue glowing dimly when the universe is 1,000,000 times older than it is today. The neutron stars created by stellar death will persist even longer, their incredible density protecting them from all but the most exotic decay processes. These stellar remnants will continue spinning in the darkness, occasionally flaring when they capture stray matter or when their magnetic fields realign. Pulsars will keep their precise timing for eons, cosmic lighthouses sweeping their beams through empty space long after any observers have vanished. And throughout this vast timeline, black holes will grow slowly larger, gradually consuming any matter that ventures too close to their event horizons. Paradoxically, as the universe expands and matter becomes more dispersed, these gravitational giants will actually begin to shrink through Hawking radiation. The smallest black holes will evaporate first, while the supermassive ones at galactic centers will persist for timescales that dwarf even the age of stars. The final evaporation of the last black holes will mark the end of the universe's connection to stellar death. These ultimate stellar remnants will disappear in brief flashes of radiation, their mass converted entirely to energy as they complete the recycling process that began when the first massive stars collapsed billions of years ago. In a sense, this represents the final transformation of stellar matter, the last act in a cosmic drama that began with the universe's first stars. But let's return from these almost incomprehensible timescales to something more immediate and personal. Right now, as you listen to these words, stellar death is occurring throughout the universe at a rate of roughly 1 supernova per second. Somewhere in a distant galaxy, a massive star is experiencing its final moments of nuclear fusion, its iron core about to collapse and trigger one of nature's most spectacular explosions. The light from that explosion is already racing through space, carrying news of stellar death across billions of light years. If the supernova is pointed in our direction, that light might reach Earth in a few billion years, adding its brief brightness to the night sky, visible to whatever creatures might exist then. The heavy elements created and scattered by that explosion will enrich the interstellar medium of its host galaxy, potentially becoming part of future planetary systems and, perhaps, future life. This constant background of stellar death and renewal provides a kind of cosmic heartbeat, a rhythm that has persisted throughout the universe's history. It's neither frantic nor sluggish, but maintains a pace that allows for the complex processes of chemical enrichment and structure formation that make galaxies, planets, and life possible. The energy released by stellar death also drives many of the most beautiful phenomena we observe in space. Supernova remnants create glowing shells of gas that can persist for thousands of years, their intricate structures revealed by the interaction between stellar debris and the surrounding interstellar medium. These cosmic flowers bloom in the aftermath of stellar death, their petals made of elements forged in stellar cores. The shock waves from supernova explosions can travel for millions of years, compressing gas clouds and triggering the formation of new stars. In this way, stellar death directly leads to stellar birth, ensuring that the cosmic cycle continues. The stars forming in these compressed regions will be enriched with the heavy elements scattered by their stellar ancestors, allowing them to create more complex planetary systems than would have been possible in earlier cosmic epochs. Some of the most spectacular objects in the night sky owe their existence to stellar death. The Orion Nebula, visible to the naked eye as a fuzzy star in Orion's sword, is a stellar nursery where new stars are forming from gas enriched by previous generations of stellar death. The bright young stars illuminating the nebula are themselves massive enough to eventually die in supernova explosions, continuing the cycle of stellar death and rebirth. The Ring Nebula in the constellation. Lyra shows us stellar death in action, a planetary nebula created when a sun-like star gently expelled its outer layers. At the center of this cosmic smoke ring sits a white dwarf, the hot core of the original star, slowly cooling in the darkness. This is a preview of our own sun's eventual fate, still billions of years in the future. The Crab Nebula represents a more violent form of stellar death, the expanding remnant of a supernova explosion witnessed by Chinese astronomers nearly 1,000 years ago. At its heart spins a pulsar, a neutron star rotating 30 times per second and sweeping beams of radiation across space like a cosmic lighthouse. The nebula itself glows with the energy of charged particles, accelerated by the pulsar's intense magnetic field. These objects remind us that stellar death is not an abstract concept, but a visible, ongoing process that we can observe directly. Every clear night, amateur astronomers with modest telescopes can see the remnants of dead stars scattered across the sky. Professional observatories monitor stellar deaths in real time, catching supernovas as they explode and tracking their evolution over months and years. As we reach the end of our gentle journey through stellar death and cosmic transformation, I hope you're feeling a profound sense of connection to the universe around you. We've traveled from the nuclear furnaces at stellar hearts to the event horizons of black holes, witnessing how stars transform themselves and everything around them through their magnificent final acts. Remember that you carry within yourself the legacy of countless stellar deaths. Every breath you take, every heartbeat, every thought drifting through your mind as you settle into sleep tonight is made possible by stars that lived, died, and scattered their treasures across space, billions of years ago. You are not just in the universe. You are the universe, temporarily arranged into something beautiful and aware. So as you drift off tonight, know that somewhere above you, ancient light continues its journey from distant stellar deaths, carrying stories of transformation and renewal across the cosmic dark. The same elements that once burned in stellar cores now flow gently through your veins, connecting you to the grandest cycles of creation and destruction in the cosmos. Sweet dreams, fellow stardust, until we meet again among the gentle mysteries of space and time.